This confidential technical report examines a complete communication and intelligent agent concept across ocean and subsea environments, the maritime surface, land and underground infrastructure, air, near space, and space. Its scope includes semiconductor families, operational radio systems, alternate communications media, current commercial and government use, compatibility constraints, engineering requirements, and verification priorities. The governing principle is evidence discipline. A component specification proves only the functions stated for that component. A system case study proves only the described system use. Neither, by itself, proves that a complete TL Tedford Enterprises architecture has been integrated, fielded, certified, purchased, or endorsed. Similar capability also does not establish electrical, waveform, software, security, safety, or regulatory compatibility. Those questions are settled through interface control documents and testing. The central finding is direct. No single transceiver repeater chipset performs the entire TL Tedford Enterprises mission. Commercial technology supplies most individual building blocks, but an intelligent agent must be engineered as a complete system. It requires multiple radios and antennas, processors and routing software, positioning and timing sensors, protected identity and key storage, power management, environmental protection, and mission applications. The market already demonstrates self-forming mobile mesh communications, multi-band software-defined radios, satellite navigation and inertial navigation, real-time kinematic positioning, local ranging, atomic clock holdover, vehicle, aircraft, and ship state broadcasting, collision warning logic, secure device identity, low-power wake-up radios, cellular and direct-to-satellite backhaul, voice, text, video, medical data transport, and underwater acoustic and optical communications. Strong commercial analogs include Persistent Systems Wave Relay, Silvus Streamcaster, Doodle Labs Mesh Writer, Rayjant Kinetic Mesh, Vehicle-to-Everything Systems, Aircraft ADS-B, Maritime AIS, Utility Field Area Networks, Ultra-Wideband and Bluetooth ranging, GNSS and inertial fusion, and precision network timing. These reduce component feasibility risk. They also introduce competitive, prior art, interoperability, and freedom to operate questions. The clearest potential differentiation lies above the basic radio layer. Agent placement and interaction, cooperative positioning, navigation and timing, predictive safety, trusted cross-domain gateways, medical and emergency orchestration, and mission-level decision logic. The statement that most required parts already exist is defensible. The statement that 80% of the finished system already exists cannot be objectively verified until there is a controlled system requirement specification, reference architecture, bill of materials, interface definitions, and measured test results. A critical boundary must remain visible. United States Patent 12,142,143b1 is titled Vehicle Alert System and Method of Use. The granted claims describe device-to-device digital addressing, GPS position, sensors that detect shapes and road surfaces, situational awareness alerts, wearable vital signs transmitted to medical personnel or a facility, a display, and voice and text sharing. Later company proposals include buried roadway nodes, a self-healing mesh, satellite-independent high-precision positioning, atomic ground timing, predictive anti-collision concepts, automatic emergency routing, artificial intelligence decision support, land, air, sea, space, subsea coordination, quantum-resistant security, and electromagnetic pulse resilience. These later integrated architecture and performance claims require formal design records, prototypes, measured testing, independent validation, and additional legal analysis. This technical narration is not a legal opinion concerning ownership, infringement, validity, export control, or freedom to operate. To understand the system, the device roles must be separated. A radio frequency transceiver generates, transmits, receives, converts, and demodulates waveforms. It does not automatically provide routing, identity, mesh networking, positioning, timing, trust, or mission intelligence. An amplify and forward repeater receives a waveform, amplifies it, and rebroadcasts it. It can repeat noise and interference, and normally has no packet knowledge or user identity.
A regenerative repeat decodes, repairs or verifies, remodulates, and retransmits a signal. That adds protocol dependence, processing, and latency. A packet layer reads addressing and forwards data, but becomes self-healing only with topology discovery, routing, security, and failure recovery. A mobile mesh router links moving peers and reroutes traffic when topology changes, but it does not inherently deliver accurate positioning, certified collision avoidance, medical authorization, or cross-domain media conversion. A gateway connects bands, protocols, physical media, security domains, and outside networks, but must apply explicit translation rules. A software-defined radio enables configurable radio frequency and baseband behavior within hardware limits. It does not establish lawful emissions, interoperability, cybersecurity, spectrum authorization, or environmental qualification by itself. The proposed intelligent agent is therefore an architecture, not a capability proven by identifying one compatible semiconductor.
Compatibility is a qualification result, not a marketing adjective. Spectrum review covers frequency, authorized bands, transmit power, occupied bandwidth, duplexing, spurious emissions, coexistence, and interference. Waveform review covers modulation, coding, framing, addressing, timing, retransmission, discovery, routing, quality of service, and broadcast or multicast behavior. Radio frequency hardware review covers impedance, filters, low noise and power amplifiers, antenna ports, isolation, duplexers, switches, phase noise, noise figure, and dynamic range. Data and processor interfaces include PCI Express, USB, Ethernet, SPI, UART, secure digital I/O, memory, interrupts, and driver support. Positioning and timing qualification includes clock accuracy, timestamp location, synchronization, holdover, ranging calibration, coordinate reference, integrity, uncertainty, and spoofing or jamming response. Mobility covers relative speed, Doppler, handoff, neighbor change, routing convergence, blockage, multipath, and air-to-ground or space-to-ground dynamics. Cybersecurity requires hardware root of trust, secure boot, signed updates, encryption, authentication, protected keys, enrollment, revocation, attestation, and compromised node isolation. The review also measures throughput, end-to-end latency, jitter, packet loss, hop count, density, route recovery, congestion, power, thermal state, environmental exposure, safety and regulation, lifecycle, supply chain, counterfeit controls, firmware maintenance, vulnerability response, and obsolescence. There are 5 compatibility classes. Class 1 is directly compatible after ordinary configuration. Class 2 is compatible through a defined gateway or bridge. Class 3 is compatible only after material hardware, waveform, driver, security, or enclosure engineering. Class 4 is not directly compatible because the physical medium or mission constraint differs. Class 5 has insufficient public evidence to classify. The first-ranked capability is self-forming, self-healing mobile mesh. Persistent Systems MPU-5, Silva Streamcaster, Doodle Labs MeshWriter, and Rajant Breadcrumb already provide moving peer-to-peer networks and rerouting. They are used by military users, first responders, unmanned aircraft, unmanned ground and surface vehicles, robots, mines, ports, rail, and industrial vehicles. This directly aligns with intelligent agents, a global mesh concept, group cohesion, local continuation without towers, disaster communications, and anti-collision missions. Yet a worldwide cross-vendor mesh with common identity, cooperative positioning, navigation and timing, deterministic safety behavior, and assured scale remains unproven. Second is position, velocity, identity, and hazard broadcasting. NXP SAF 5400 vehicle-to-everything technology, Qualcomm vehicle-to-everything platforms, Aviation ADS-B, and Maritime AIS exchange current state and traffic information. They provide the closest direct matches to device communication, situational awareness, alerts, and accident prevention functions. Universal Authenticated Land-Air-Sea Track Exchange and Safety-Certified Autonomous Intervention require additional standards and validation. Third is cooperative ranging and local positioning. Qorvo DW3220 ultra-wideband, Bluetooth channel sounding, and Bluetooth direction finding are used for digital vehicle keys, consumer trackers, warehouses, worker safety, indoor navigation, robots, and industrial vehicle systems.
They enable neighboring agents to contribute distance, direction, and confidence measurements when satellite positioning is weak or absent. But they do not prove 2 centimeter wide area positioning. Surveyed anchors, clock calibration, geometry, filtering, multipath control, and integrity monitoring are required. Fourth is GNSS, real-time kinematic positioning, inertial navigation, and deadlocking. U-Block's ZUF9R, STMicroelectronics Teseo VIC3D, and Septentrio Mosaic X5 support precision navigation and continuity through satellite outage or degraded reception. Inertial navigation drifts over time, and these products alone do not create satellite-independent global navigation. Fifth is distributed timing and holding. Microchip chips give atomic clocks and precision timing protocols support.
6th is multiband software-defined radio and wideband regenerative repeating. Analog devices ADRV 9002 and AD9361, Texas Instruments AFE 7950, Lime Microsystems LMS 7002M, and AMD radio frequency system-on-chip platforms support reconfigurable radios, multiband fallback, field upgradable waveforms, frequency agility, radar, avionics, satellite communications, signals intelligence, and test systems. Antennas, filters, amplifiers, processors, routing, lawful spectrum use, waveform software, certification, and security remain separate design work. 7th is high mobility MIMO, adaptive links, and electronic warfare resilience. Persistent Systems, Silvus Technologies, and Doodle Labs demonstrate mobile radios for soldiers, vehicles, unmanned systems, tunnels, cities, maritime operations, and public safety. They support adaptation of paths, frequencies, polarization, and routes. Manufacturer claims must be verified against defined adversary waveforms and government test conditions. 8th is multi-protocol gateways and automatic transport selection. NXP IW612, Texas Instruments CC1354P10, Nordic multi-protocol devices and operational gateways connect short-range sensors, long-range mesh, broadband payloads, cellular, satellite, and command systems. Hardware coexistence does not automatically translate application meaning, addressing, trust, priority, or safety policy. 9th is secure identity, encryption, and protected key storage. Secure elements such as NXP EdgeLock SE050 support digital addressing, agent identity, medical privacy, military trust, secure boot, and signed updates. They do not replace a complete public key infrastructure, enrollment, revocation, attestation, update governance, compromised node isolation, or defined post-quantum migration. 10th is edge computing, artificial intelligence, and sensor fusion. AMD RFSoC technology, Nordic NRF54H20, Silicon Labs EFR32MG26, and external application processors support predictive vectors, collision risk, distributed awareness, route decisions, and decision assistance. Processing hardware does not provide validated models, training evidence, deterministic fallback, functional safety, or acceptable false alert rates. 11th is store and forward and disruption-tolerant networking. Internet Engineering Task Force Bundle Protocol version 7 can improve delivery probability across space and intermittently connected networks. It supports disaster, remote, obstructed, and cross-domain delivery when no continuous end-to-end path exists. It cannot provide immediate millisecond collision warning during a disconnected internet. 12th is ultra-low power, wake-up radio, and energy hoist. STMicroelectronics STM32WL3, Atmosic ATM34, Nordic and Texas Instruments low-power devices support tags, wearables, warehouse sensors, smart city devices, appliances, tracking products, dormant roadside sensors, emergency nodes, and long-endurance field equipment. Very low power, high bandwidth, long wake, low latency, and continuous operation cannot all be maximized at the same time. 13th is long-range sub-gigahertz infrastructure. Semtech LR1121, Morse Micro MN8108 Wi-Fi Halo, and Wison Field Area Network Systems support smart meters, utilities, streetlights, agriculture, wildfire detection, pipelines, smart cities, sparse road corridors, fixed infrastructure, and road 16th is voice, video, text, position, and sensor transport. Persistent Systems, Silvus, Doodle Labs, and Radiant Internet Protocol networks support tactical awareness, robots, public safety, industrial monitoring, shared maps, cameras, sensors, group cohesion, emergency communications, and common situational awareness. Quality of service policy must properly prioritize collision warnings, emergency messages, command traffic, medical data, voice, video, and routine telemetry. 17th is automatic emergency notification and medical information. Bluetooth to cellular medical gateways and European emergency call systems already support remote patient monitoring, electrocardiography, oxygen saturation, blood pressure, glucose, falls, vehicle crash notification, wearable vital signs, medical preparation, automatic emergency notification and response routing. Electronic health record identity, consent, privacy, clinical validation, medical regulation, and emergency service integration remain outside the radio. 18th is underwater and subsea communications. Teledyne Benthos acoustic modems, Sonardyne Modem 6, and Sonardyne Bluecom optical systems serve autonomous underwater vehicles, remotely operated vehicles, offshore infrastructure, subsea sensors, surface vessels, and data recovery. Ordinary radio frequency does not propagate effectively through seawater. An acoustic or optical underwater link must connect through a buoy, unmanned surface vessel, ship, offshore platform, or shore station to reach the radio mesh. 19th is conventional repeaters, small cells, and fifth-generation relays. Texas Instruments AFE79XX wideband repeater architectures, 3GPP integrated access and backhaul concepts, network-controlled repeaters, and Ericsson Radio Dot can extend selected links and fill coverage gaps in indoor cellular service, remote sectors, venues, and capacity expansion. A conventional repeater normally has no agent identity, cooperative positioning, navigation and timing, routing intelligence, sensor fusion, or mission reasoning. 20th is environmental, radiation, and electromagnetic pulse resilience. Texas Instruments AFE7950-SP radiation-hardened radio frequency sampling, rugged tactical enclosures, and critical infrastructure protection practices can support space hardware and harsh military or industrial environments. Radiation-hardened silicon is not equivalent to electromagnetic pulse protection. Antennas, power, grounding, cabling, surge protection, enclosure, installation, and spares determine system resilience. The Semiconductor Register compares representative active families and their possible roles. It does not declare that any operational radio contains a particular semiconductor, because vendors often do not disclose internal bills of materials. For broadband and software-defined radio, Analog Devices ADRV9002 provides a 30 MHz to 6 GHz dual transmit and receive radio platform with frequency agility. AD9361 is a mature programmable 2-channel radio frequency transceiver used in software-defined radio, base station, unmanned aircraft, and instrumentation designs. Texas Instruments AFE7950 supplies 4 transmitters, 6 receivers, wide instantaneous bandwidth, direct RF sampling, and low-latency receive-to-transmit loopback. AFE7950-SP is its radiation-hardened variant for space and high-reliability environments. Line Microsystems LMS7002M provides a field-programmable 2-transmit, 2-receive MIMO radio from 100 kHz to 3.8 GHz. AMD RF SoC technology combines high-speed converters, programmable logic, ARM processors, and optional forward error correction resources. These are Class 3 integration platforms, high capability but still requiring RF design, processing, software, routing, security, power, thermal management, assurance, and certification. For low-power companion connectivity, Texas Instruments CC1354P10 supports sub-gigahertz and 3.4 GHz multi-protocol operation, including Bluetooth, Web, Gigabit, Wi-Fi, and proprietary links. NXP IW612 and OW612 integrate Wi-Fi 6, Bluetooth For reach, positioning, timing, sensing, and trust, additional components serve focused roles. Nordic NRF 9151 integrates LTE for machines, narrowband Internet of Things, non-terrestrial network capability, GNSS, and a microcontroller for optional cellular and satellite-connected remote assets. Sony Altair ALT1350 supplies low-power wide-area cellular and non-terrestrial network architecture. Semtech LR1121 supports multi-band LoRa and long-range frequency-hopping spectrum across sub-gigahertz, 2.4 GHz, and satellite S-band. Morse Micro MM8108 supports sub-gigahertz Wi-Fi Halo for higher-rate IP cameras, industrial devices, and infrastructure links. Qorvo DW3220 supplies secure ultra-wideband two-way ranging and angle support. u-blox ZF9R combines multi-band real-time kinematic GNSS, inertial fusion, and dead reckoning. Septentrio Mosaic X5 provides multi-constellation GNSS, interference mitigation, spoofing awareness, and high-precision positioning. ST Teseo VIC3D combines GNSS, a 6-axis inertial measurement unit, and dead reckoning. Microchip SA65 provides low-power chip-scale atomic clock holdover. The ZL3793 family supplies precision time protocol and synchronous Ethernet timing synchronization. NXP SAF 5400 provides automotive-qualified dedicated short-range vehicle-to-everything communication with high safety message verification capacity. NXP SAF 85XX provides 77 GHz automotive radar for object, range, speed, and collision risk sensing. Qualcomm vehicle-to-everything and automotive modem radio platforms add road safety, cellular backhaul, high-precision positioning, and telematics options. NXP EdgeLock SE050 provides a tamper-resistant secure element for protected keys, identity, attestation, and cryptographic functions. These are mostly Class 2 or Class 3 capabilities. They must be integrated with gateways, interfaces, security policy, time distribution, calibration, sensor fusion, and environmental qualification. They do not independently create a complete global mesh. Finished operational systems provide an equally important layer of evidence. Persistent Systems Wave Relay MPU5 is the strongest single commercial analog for the tactical agent communications layer. It demonstrates self-forming and self-healing mobile ad hoc networking, MIMO, voice, video, text, positions, sensors, shared maps, edge compute, encryption, electronic warfare functions, and optional 5th-generation cellular or satellite transport. It is used by military forces, first responders, strategic asset convoys, unmanned systems, robots, subterranean, urban, and maritime missions. It does not establish TL Tedford Enterprises cooperative positioning, navigation, and timing or patent ownership. Silvus Technologies Screencaster provides high-mobility MIMO mobile ad hoc networking, video, voice, IP data, unmanned system integration, and contested environment operation for defense, law enforcement, public safety, unmanned aircraft, ground systems, and sensors. Doodle Labs MeshWire offers self-forming multi-band mesh, stated configurations up to 80 megabits per second, long-range air links, interference avoidance, and compact unmanned system form factors. It has been used in work involving Teledyne FLIR Skyranger aircraft, U.S. Army short-range reconnaissance, autonomous surface vessels, and commercial unmanned aircraft. The Jaunt Kinetic Mesh Breadcrumb provides peer-to-peer multi-radio industrial mesh with distributed routing and no single central failure point for mining, ports, rail, energy, warehouses, autonomous machinery, construction, utilities, and defense. Teledyne Ventos shows acoustic command and data between subsea assets and surface gateways. Solardyne Modem 6 and Viewcom show that underwater missions require different modalities: acoustic links for long-range and low-rate, and optical links for short-range higher-rate transfer. Ericsson Radio Dot and 5th-generation cellular repeaters extend indoor access and coverage through operator infrastructure, but they are not tower-independent mobile mesh or cooperative PNT. Texas Instruments AFB79XX illustrates a genuine chipset-level repeater building block, requiring substantial external digital, radio frequency, network, and mission engineering. A single physical waveform cannot efficiently cover every environment. The defensible global mesh architecture is a federation of domain-appropriate links joined by trusted gateway agents. Each gateway must preserve identity, timestamp, position uncertainty, priority, authorization, and data provenance while translating transport. In the subsea domain, the preferred combination is acoustic modem for range, optical modem for short-range high data rate, inertial navigation, pressure sensors, and sonar. Acoustic and optical links terminate at a buoy, unmanned surface vessel, ship, offshore platform, or shore station. Radio frequency chipsets cannot substitute for underwater acoustic and optical physics. On the maritime surface, mobile ad hoc network radio, AIS, GNSS, and inertial sensors, plus available satellite or cellular backhaul, serve vessel awareness and communication. A surface gateway combines underwater tracks, ship identity, weather, video, and command traffic before relaying to land, air, or satellite. AIS aids awareness, but it is not complete collision avoidance or trusted military networking. On land and in subterranean corridors, tactical mobile mesh, industrial kinetic mesh, roadway agents, WISON, sub-gigahertz telemetry, ultra-wideband ranging, GNSS, inertial navigation, and precision timing can operate together. Land agents offer the densest opportunity for surveyed anchors, local power, maintenance, and connections to responders and infrastructure. Buried life, radio propagation through pavement and soil, drainage, antenna design, maintenance, and electromagnetic pulse protection require corridor testing. In the air domain, airborne mobile mesh, ADS-B, aviation GNSS and inertial navigation, air-to-ground radio, radar, and optional cellular or satellite backhaul enable aircraft and unmanned systems to serve as moving relays. They can provide altitude, line-of-sight extension, imagery, and tracks. Aviation integration requires certified equipment, spectrum authorization, safety assessment, and strict separation between advisory and control functions. Near-space platforms can use high-altitude radio, directional links, GNSS and inertial navigation, precision timing, radiation-aware components, and disruption-tolerant network to provide broad regional coverage and gateway service. Their environmental conditions, link budgets, Doppler, power, thermal design, and licensing differ from ground radios. In space, radiation-qualified RF conversion, beamform, satellite communication waveforms, atomic or discipline timing, onboard processing, and disruption-tolerant network can provide optional reach, sensing, and backhaul. They must not become mandatory for local terrestrial continuity. Radiation-hardened components do not automatically make a complete space-qualified system. Latency, orbital dynamics, ground stations, export control, and debris safety apply. At the cross-domain command and medical service level, secure gateway, identity, quality of service, data link, electronic health record interfaces, emergency service interfaces, and policy enforcement connect mission users, hospitals, dispatch, traffic systems, utilities, and command centers. Authorization, privacy, safety, and subject to interoperability remain application layer responsibilities. The report identifies existing external use threats and public The complete concept coverage must distinguish expressly described functions, enabling technologies, and later proposals requiring proof. Strongly aligned issued patent functions include device-to-device digital addressing, shared alerts and situational awareness, GPS position and local continuity, shape and road surface sensing, voice, text, and display, wearable vital signs and medical transmission, and motorcycle or military group cohesion. Later company proposals require additional evidence. These include a buried self-healing roadway mesh, 2-centimeter satellite-independent positioning, navigation, and timing, 2 to 3 millisecond decisions and sub-10 millisecond secured latency across a multi-hop global mesh, 10 gigabit per second capacity with more than 500 connections per agent, verified post-quantum security, automatic emergency notification and optimized routing, smart traffic, parking, and transit integration, TMOA defense and TVA civilian anti-collision concepts,
a global land, air, sea, space, subsea agent network, and electromagnetic pulse-resilient infrastructure. Commercially demonstrated building blocks include transmitting and receiving across numerous radio bands and protocols, amplify and forward and regenerative repeating, self-forming and self-healing mobile packet routing, MIMO, adaptive links, frequency agility, and beamforming in appropriate products, voice, text, video, position, and sensor transport, local ultra-wideband and Bluetooth ranging, GNSS with real-time kinematic correction, inertial navigation, and dead reckoning, atomic clock holdover and precision network synchronization, secure elements, encryption, authenticated updates, and device identity, cellular and non-terrestrial backhaul, automatic vehicle emergency calls and connected health gateways, aircraft and ship state broadcasting, underwater acoustic and optical links, and radiation-hardened RF conversion for selected space applications. Claims requiring controlled proof include one universal intelligent agent for every domain and mission, one global cross-vendor self-healing network with common trust and deterministic behavior, wide area 2-centimeter positioning without satellite assistance, 2 to 3 millisecond secured end-to-end decisions across multiple mobile hops, 10 gigabit mobile mesh performance with more than 500 simultaneous connections, independently verified 99.99 or 99.995% system availability, 25 to 30-year buried life, a deployed verified post-quantum implementation, complete electromagnetic pulse survivability of enclosures, antennas, power, cabling, gateways, and connected infrastructure, safety-certified predictive collision avoidance across land, air, and maritime domains, authorized automatic retrieval of medical records, and independent government deployment, procurement, or endorsement of the complete Later architecture. The first credible prototype should be modular and should use commercially available subsystems. A custom all-in-one semiconductor should not be the first development objective. The reference architecture should permit multiple vendor choices at every layer, avoiding reliance on a single supplier. At its core is a broadband mobile network radio. For a first demonstration, buy or partner with an operational mobile ad hoc networking vendor, or use Analog Devices or Texas Instruments radio frequency silicon with AMD or another processor for a Leader custom radio. This layer carries primary voice, video, position, sensor, and command traffic. A low-power companion radio can use Texas Instruments CC1354, NXP IW612 or RW612, Nordic NRF54, Silicon Labs EFR32MG26, or ST-STM32WL3 for wearables, sensors, infrastructure control, wake-up, and local device connectivity. A relative ranging subsystem can use Qorvo DW3220 ultra-wideband with optional Bluetooth channel sounding to contribute enable range, direction, secure proximity, and cooperative positioning measurements. Absolute and inertial navigation can use Septentrio, U-Blocks, or ST-GNSS and inertial devices with a mission-appropriate inertial measurement unit, providing satellite navigation when available and dead reckoning during outages. Timing requires a microchip chip-scale atomic clock or precision oscillator, plus precision time protocol hardware time stamping and distribution. Security requires a secure element or equivalent, trusted boot, signed software, identity enrollment, revocation, attestation, encrypted storage, and cryptographic agility. The edge computer is mission selected with optional AMD RF SoC for high-rate signal processing. It performs routing, sensor fusion, predictive vectors, quality of service, data labeling, and gateway logic. Optional wide area backhaul can use Nordic NRF9151, Sony Altair, Qualcomm Cellular, commercial satellite, or other approved transport, without making outside infrastructure mandatory for local operation. Radar, LiDAR, camera, infrared, weather, road, vehicle, wearable, medical, sonar, and mission sensors supply the awareness data that communications hardware alone cannot create. Domain-specific battery, vehicle, grid, or harvested power, protected power, thermal design, filters, antennas, grounding, sealing, and maintainability determine real-world endurance, range, environmental performance, safety, and resilience.
The verification program begins with a requirements baseline. Define domains, range, bands, data types, node density, latency, positioning accuracy, integrity, power, security, environmental, and regulatory constraints. Freeze measurable definitions before selecting parts. Second, perform bench integration. Connect radios, processors, secure elements, GNSS, inertial sensors, ranging, and timing. Verify timestamping, drivers,
secure boot, update process, packet priorities, and failure logging. Third, run a 10 to 20 agent field demonstration. Use moving land agents, one fixed gateway, and one airborne relay, with satellite and cellular disabled for selected tests. Measure route formation, route repair, end-to-end latency, throughput, position error, timing, power, and alerts. Fourth, conduct a 50 to 100 agent corridor demonstration. Introduce congestion, interference, moving obstacles, GNSS degradation, node loss, malicious or invalid data, and emergency traffic priority. Fifth, run a cross-domain demonstration. Add an unmanned aircraft, maritime surface gateway, underwater acoustic or optical endpoint, and optional non-terrestrial network link. Preserve identity, timestamp, uncertainty, and priority across every gateway. Sixth, obtain independent laboratory and government range validation for electromagnetic compatibility, environmental exposure, cybersecurity, electronic warfare, functional safety, medical data handling, and electromagnetic pulse system testing as applicable. Seventh, prepare controlled pilot production with a controlled bill of materials, domestic supply review, manufacturing test procedures, configuration management, a vulnerability response process, and a product lifecycle plan. Acceptance measurement must show how isolated agents discover neighbors, authenticate, and form routes. It must show route recovery after removal, movement, power loss, interference, or compromise. It must report one-way application-to-application latency by priority, hop count, payload size, encryption state, congestion, and mobility. It must measure sustained useful payload throughput, not only radio link headline rate. It must report horizontal, vertical, and relative positioning error with confidence bounds under clear sky, urban multipath, tunnels, indoor conditions, jamming, and satellite off conditions. It must quantify positioning integrity, including probability of undetected hazardous error, alarm limits, time to alert, and response to spoofed or inconsistent sources. It must measure timing offset, drift, holdover duration, path calibration, resynchronization, and hostile time source rejection. Predictive safety validation must include time to collision accuracy, warning timeliness, false positives, false negatives, missed detections, sensor disagreement, and safe fallback. Cybersecurity evidence must cover secure boot, identity cloning resistance, credential revocation, update rollback prevention, penetration testing, compromise containment, and log integrity. Defined electronic warfare testing must assess noise, deceptive signals, waveform-specific attacks, congestion, and spectrum denial. The evidence program must also measure average and peak energy, sleep and wake behavior, thermal state, degraded power operation, temperature, water, dust, vibration, impact, corrosion, pressure, radiation where applicable, surge, lightning, electronic magnetic pulse response, control overhead, routing stability, compute and memory use, connection limits, multicast performance, failure domains, and cross-domain preservation of source identity, timestamp position uncertainty, classification, authorization, priority, and provenance. Every agent requires a unique hardware-backed identity and an auditable enrollment history. Communications confidentiality, integrity, origin authentication, replay protection, and authorization must be separated and tested individually. A compromised agent must be revocable without disabling the network. Software and configuration updates must be signed, version controlled, rollback protected, and recoverable. Post-quantum security must be implemented through cryptographic agility and standards-based algorithms, not a marketing label. Medical information must be minimized, consented, authorized, encrypted, logged, and separated from general situational awareness data. Artificial intelligence recommendations must preserve source data, uncertainty, model version, a reasoning trace appropriate to the safety case, and human override where required. Collision warning and navigation functions must fail safely when position, time, identity, or sensor integrity is uncertain.
One DOE's ability to pass packets does not permit the indiscriminate merging of military, public safety, civilian transportation, medical, maritime, aviation, and space security domains. The defensible technical position is not a single new radio ship. It is a system of systems architecture combining commercially mature communications, sensing, positioning, timing, security, computing, medical, emergency, and domain-bridging technology into intelligent agents operating under a common mission doctrine. The high-value work remaining is controlled agent architecture, cooperative positioning, navigation and timing with integrity, blend of trust, predictive safety logic, security and language security,
The strongest development strategy is modular. Purchase or partner for mature radio and mesh functions during early demonstrations. Focus proprietary engineering on agent orchestration, cooperative positioning, navigation and timing, predictive safety, trusted multi-domain coordination, automatic emergency and medical functions, and the placement and operational doctrine that bind the system together. Future government and investment papers should describe the technology as a system of systems architecture, supported by existing components and targeted new integration. That position is more technically credible than presenting the program as a single revolutionary transceiver repeater chipset. It makes the remaining development, evidence, intellectual property, qualification, and funding requirements visible. This controlled record retains the architecture definitions, 20 ranked capability areas, semiconductor options, operational system comparisons, existing uses, multi-domain compatibility, patent boundary, proven and unproven functions, modular reference architecture, security requirements, acceptance measurements, strategic implications, and primary sources. Any external distribution should preserve the evidence labels, engineering limitations, and patent boundaries together with the capability analysis. T.L. Tedford Enterprises Intelligent Agents, a modular, measured, and verifiable path from commercial building blocks to trusted multi-domain capability.